So welcome. This is our first live episode of Self-Directed Research Podcast. Thank you.
Thank you for showing up. It's nice to see you all.
Yeah, thank you for showing up. Who here has listened to the Self-Directed Research Podcast before? All right. We got some of the audience.
Up.
So I'm James Munns. I'm going to be your host today. Self-Directed Research Podcast is it's funny because it kind of started as, hey, what if we did conference talks, but someone presents and we have the peanut gallery there to actually ask questions. So Amos and myself got together and we take turns giving presentations. So there's going to be me presenting today about type erasure in Rust and Urgot. And then Amos still hasn't told me what the presentation is tomorrow, but I've heard there's a lot of preparation and there's been some practice rounds. So I think tomorrow's going to be interesting to come show up to you as well.
Yeah.
So if you haven't seen it, come. We publish our stuff on YouTube. We have a podcast feed. We say sdr-podcast.com/episodes roughly 100 times. But
because we have slides, just like there's your problem. We like to have slides, and we try to describe out loud what's on the slides, and sometimes we forget. So it's always good to have the slides alongside.
Excellent. Well, I have 56 slides today, so we better get started because we need time for both me and Amos to talk. But today I'm going to be talking about type erasure in Rust in Urgot. So Urgot is a messaging library that I've been working on. Ooh, got lightning. Urgot is a messaging library that I've been working on for networking with very tiny devices. And if you have listened to the podcast, you've probably heard me talk about a lot of building blocks of Urgot. And today we're going to look at sort of the deepest, darkest, unsafest part of Urgot. And there's no one I'd rather do it with than you, Amos.
Thank you. It's fun because the podcast is kind of a recorded history of you building all the parts building up to this thing.
You can see for both of our projects like how we got to what we're currently working on by looking at the episodes. But Urgot's a messaging library for both STUD, like desktop and server devices, as well as no STUD devices, which means it needs to work even if you don't have an allocator and if you're running on a device that only has like 8K of RAM. And unlike TCP/IP, it actually is very opinionated in that you have type-safe sockets. So when you open up a socket, it's not necessarily here's a stream of bytes or here's frames of bytes like TCP or UDP. It goes, I'm receiving this Rust data type or I'm sending this Rust data type. So in essence, it actually kind of acts a bit more like channels than TCP/IP sockets where it handles the transport, but you're in charge of the data. Yeah. So there's a big snippet of code. Don't worry about understanding all of it, but this is sort of my proof that if you were to run this on a microcontroller, you could open up a server endpoint that takes some Rust data, like here an F32, and that function might return a U64. So when you're writing these sort of server functions, it's maybe more a bit like Tower or something like that, where you go, hey, I have a service that takes this data and gets this out, and all of this works even on a little microcontroller and things like that. And so like Urgot, because it is using it's using type-safe, and that might go from one device to another, we have some concerns of how do we get data from here to there. So unsurprisingly, I use serday for ser and day. So when we want to serialize and deserialize things, it just uses the plain old serday crate. I write a data format called postcard, which is a very compact binary format. If you've used embedded, you've probably seen postcard around because a lot of folks use it. And I use this other crate that I have called postcard schema, which I've built my own reflection at home so that I can take a reflection in a schema of a message type, and then I can crush that down into a hashed message ID.
Was that the compile time crimes episode?
Yes. So if you want to go back to the compile time crimes episode, this is where like postcard schema came from, because I take all of those schemas, build them at compile time, then hash them at compile time. So on our itty-bitty little microcontroller devices, they just get an 8-byte value, and they don't have to think very hard about it. It's a number that they think maps to whatever they're doing. So Urgot lets you send and receive locally. So if you like actor model stuff, you can send stuff locally and receive it locally, and that's interesting. And similarly, if we have our little embedded device hooked up over a USB port or something like that, I can send messages over there and receive them back, and they just magically work. But because we have these tiny devices, it has to be efficient as possible. So we need to beg, borrow, cheat, and steal as often as we can to make it as efficient as possible. So
how many of those are keywords in Rust?
They all should be reserved at this point. But we can cheat and do things like, hey, if you're sending from local to local, we're just not going to serialize at all. We'll just treat this like a normal channel, and I'll go, hey, this is for you. Here, you can have it. And instead of like doing the whole round trip of that, I can just hand it over to another socket. And this is what like the main interface in Urgot is. It's our friend, the socket. Whenever we want to receive data, it's like the little mailbox we have in our house. It's just where messages come in, and it's our main interface for things like this. And this is where things get tricky, because each of those sockets can be a different type. Because I said that we're type safe. And we have sockets, and they're type safe, which means we have a socket of one kind and a socket of another kind. So we go, okay, it's going to be generic or something. And actually, because I want this all to work on embedded and desktop, each socket can have different storage. You might want to use the heap on the desktop or some static collections on my microcontroller. So,
James,
yes.
How many time parameters do you have on this?
I've done some things to hide them.
Okay, carry on.
And so you don't have to worry about a heap. I pin my socket. So a cool thing about pinning is that you can guarantee that it doesn't get dropped without running the destructor. And so you can say, hey, this is where my socket is, and the storage is here, and it's pinned right here inside of my task. And on embedded, this means in a static task allocation, or if you box your task or whatever, it goes there. And this is where things start going off the rails, because on embedded we don't have collections. I have to have some way of having a variable and dynamic number of types. And so if you've listened to the last SDR podcast episode where I talk about intrusive links lists,
I did.
You did. You were there, in fact. I have an intrusive link list of all of my sockets, and because they're pinned where they are, I can guarantee that they don't get dropped without. I can't invalidate those pointers, at least not safely. And so I've got this nice little link list of sockets where they live in their tasks. Now, all these sockets have some stuff in common. And so like if we have them in an intrusive linked list, they're going to have some kind of common header, at least the linked list. So intrusive linked lists are where you have a header and the data. So you don't have like a pointer to all the nodes and then each of those nodes point to the data. It's all just smushed together, and the linked list pointers live at the top of that, so you can bounce around the items. So they've got that, which makes sense because they're in a linked list. And then I've got socket metadata. So this is like the port number, what kind of data it is, should this socket be discoverable, and this is all stuff that we use for routing. When someone wants to go, hey, I'm a mailman and I want to deliver this message, how do I find the socket that I want? And we just look at this metadata and we go, oh, this message goes with this socket. I should put it here. And then they have a vtable. And the vtable is how we allow all of these different sockets to be totally different under the hood, but the net stack doesn't necessarily have to care about that. And if the word vtable doesn't strike fear in your heart yet, I'm essentially hand-rolling what din trait does. So when you can have a bunch of objects that have the same interface, but do things very differently.
I have to distract you. This is my job on this podcast when you're hosting. First of all, it's very fun to me watching you nail this presentation, because I have this problem all the time for my own content. I'm going to do a bunch of videos that talk about the components, and then I'm going to build it to this video that brings everything together.
Yeah.
What I have, the result is that people need to have watched the previous 15 episodes to understand what I'm talking about. So this is very fun. Also, I notice you're doing a lot of things manually. You even have the word manual on that slide. Is it even worth using Rust at this point?
So the nice part about unsafe Rust is that you can do all of your spooky things inside of the box, but you can still get the nice type safety outside of that. And the main idea is that me as the implementer of Urgot can do all these spooky unsafe things that are molten on the inside, but to all the users on the outside, you go, I have a socket that is of a type, and it's clear that when I receive, I'm going to receive messages of this type. So the answer is my hands are dirty so that everyone else's hands don't get to be dirty. Does that make sense?
I can picture the image, yes.
So let's pretend. So I said we're making manual din trait, so we're going to go metaphorical, and I'm about to start lying to you. So don't think too hard. And if you know where this I'm going to say some things and you go, wait, you can't do that. That's illegal. Don't worry about that. We'll get there. But let's pretend that we have trait socket, because we say we just want to have a socket that does stuff. Sure. So what does a socket need to do in Urgot? It's got about 4 things. So one, like I said, if I'm sending something locally, I'm passing you some own data. I have a Rust piece of data, and I'm going to hand it to you. And so we've got self of our socket. It's pinned in its place, and I'm giving you a reference of it. And we say that this type needs to be cloned. So if I'm handing it to you, you can clone it into yourself. And I've got the header of the message and a type ID. Don't worry about why I have to pass a type ID as well. And then you as a socket can either tell me, yup, it went great. I have the message. It's mine now. Lovely. Or that something went wrong. And then similarly for an error, if you tried to send something and someone's sending back an error, this is, again, I'm just handing you an owned error that says, hey, that message was refused, or we couldn't find the destination you were looking for. Here's the error.
I don't follow this one. How do you know which one to call? Do you call both in a select?
It gets delivered back to what your source address was. So when you send a message...
No. You have receive owned and receive error.
Yeah.
Do you call both at the same time? Like, you don't know when to expect an error.
The answer is it's... you would call these in different places because receive owned is from a local socket. Receive error, you only get errors from the remote interfaces. So it is also a received owned, but it's received owned of one very specific type. Yeah, and maybe it could be cleaned up, but it's one of those, this is the shape it is now.
I'm on to you.
And then we get a little interesting because if you received a message over the network, it's gonna come as bytes over the network. I say it's a strongly typed interface, but that's like a user thing. You gotta put bytes over the network at some point. So I could say that I'm going to receive of a certain type, and that type has to be deserializable. So when the external interface hands me something, it goes, here's a header and a bag of bytes. Do you like this? And then it's your job as a socket to go, yes, I could deserialize that, and I now have the data, and I'm happy. Or no, that didn't work. Or no, I have no idea what you're talking about. And then finally, what if we have types that are borrowing information? Like, let's say I want to send a message to you that has a borrowed stir in it. That's not owned. That's not tick static. So this is still serializable. So I'm going to go, here's I'm going to hand you the data, and here's a header, and there's a serialization function. Don't worry about that now. That's not going to make sense until we start looking at the spooky stuff. And similarly, I can go, here's something. You can't just take it, but you can copy it and do something with it. And then you might decide that you're happy with it or not. And interestingly, these sockets, some of them actually can work really, really different under the hood. So some sockets might decide to store data as typed information, much like a channel. So I just have my little array or my vec or vecdeck of messages, and that's great. But if you want to store those borrowed pieces of data, you can't store borrowed data because you don't know how long that's going to last. And maybe if I was Manish, I could do yoke, and I could yoke the message in and maybe but we don't have a heap anyway on my microcontroller, so that's not going to be an option.
Yoke is a crate that lets you... Essentially, when you borrow from an input, it's annoying because then you can't move the input anymore because you've borrowed from it. So yoke is like magic. And now, if you can move the input together with the things that are borrowed from it, it's very complicated. It has a bunch of traits that make my head hurt. So
yeah, my approach to this was, hey, what if we need to store borrowed data? What's a good way of making a reasonable, full, deep copy of that data? Well, you serialize it, and then you just hold on to the serialized form of it inside of the socket instead of the owned Rust data. It means it's a little less efficient because when you want to take the data out, you've got to deserialize it again, but then you can borrow from the socket because that's where the data is now, and as long as it's in the socket, I can borrow it. So you could actually sort of cheat and send borrowed data within the system, but it is going to serialize it and then deserialize it, so you have the bytes in your socket.
But you're saying sockets store data. What? Is it a queue? Are they waiting to be sent?
It's like a queue. It's like a mailbox queue, if that makes sense. So you're going to get kind of like a FIFO interface of like in the order that they were shoved into the socket. When you call receive on the socket, you're going to get data back out there. So it might be like on a desktop with a heap, you might use vecdeck for something like that. On embedded, you might use kind of like a stackful version of vecdeck, but like a FIFO of items. Okay. And then when you're storing them as bytes, you might use like a byte FIFO, like BBQ is what I use for this. That's a bit buffer queue. But you can have variable length byte chunks in a ring buffer, basically.
Didn't you write BBQ?
I wrote BBQ. I tend to use a lot of the tools that I write. So when you're in owned socket, if you receive owned, you get a type in and you store it as a type. Or if you get raw data in, you deserialize it and store it as a type. If you get an error in, you get an error. You can't accept borrowed messages because I'm in the business of storing owned things. And so we can just say, well, you don't implement that method. It's like an optional method.
Right.
And then if you're storing things as borrowed, if you are given an owned message, you've got to serialize it so you can store it in your pocket. A raw message, you just go, oh, I'm just going to copy those bytes, and it's already in the form that I want it in. If it's an error, I have to serialize that, and if it's borrowed, I serialize it. And then great, in my pocket is always the same piece of data. And this is where we get to the point where I've lied to you a lot. Has anyone caught what I've said that you can do with a trait that you can't do, or the many things that I've said you can do? Any hands?
I didn't
Amos,
get
have
into
you
the signatures,
noticed?
no.
I haven't seen any hands, so I'm good. I'm sneaky enough.
Come back. I want to see the, the methods again.
So one thing is, I said all these sockets are different types. Rust does not love storing dissimilar types or even the same type with different generics in the same collection. It gets understandably real mad about that because those are not the same types, and you can't really store them because they're totally different types once they've been monomorphized. And then also on all those receive messages, they had generic parameters on there, and nothing with a generic item on it can be DIN compatible, which is unfortunate because our sockets are always for one item, but they can all be different items.
Ah, so you switch to Swift.
Yes, yes.
It does allow you to do that.
I'm going to get Ganker on the line, and I will switch to Swift.
Clearly.
So what does it actually really look like? So the lie that I told you is we have this lovely method with a pin itself and a pointer to things, or excuse me, a reference to things and a header and things like that. The ugly truth here is a lot of non-nulls. So this is type erasure in Rust. So not only am I giving you a pointer and not a reference, I'm not even telling you what the type is. This is void star programming. You can tell that I started as a C programmer, maybe.
Is this allowed? Like non-null of okay. Non-null of empty tuple.
Yeah.
But isn't this like non-if safe or something?
You gotta change it before. Maybe this is why I'm showing it, because maybe someone smarter than me will go, hey, you're doing something illegal.
I'm not in.
It works.
I'm not in the UB work group. I'm not in like language semantics.
You definitely have to cast it to something.
I just make those people mad once in a while. I'm not part of the group.
But that's the trick: is that the socket itself knows what type it is, and it knows what type of data that it wants. And so it can go, well, you pass me a blind pointer, and so what am I going to do first thing with that? Well, I'm going to cast the this pointer back to me, and I'm going to cast the that pointer back to the message that I care about. After checking, and this is why I pass in the type ID, is because first I check, because someone could be doing something wrong, but if you know you're calling me, the pointer to me is me, and the pointer of you're passing to, if the type ID matches, then the pointer of what you're passing me to works. And then we just do a little unsafe, and hey, look, now we're kind of back to where we were lying about.
I'm thinking back on my question of like, is it still worth doing Rust?
Maybe your tolerance is different. For me, it was worth it. But
a bonus question: did you run any of this under Miri?
All of it under Miri.
All of it, really?
Yeah.
All right.
There's a lot. We'll see. I'm not following this, but most of my testing is done under Miri. I don't have like super exhaustive things, but definitely the core routing and this type punting stuff has been all passing Miri since day one. So if Miri needs to get better, maybe Miri needs to get better. But everyone, even under like strict, not stack borrows, it was tree borrows, or no, under stack borrows, it's passing. Okay, so
we have some background to give. So Miri, for those who don't know, is a tool that helps you find undefined behavior. Unfortunately, if something, so it's like an interpreter for us. It's the same one that's used for const eval. Ollie will hit me on the head if I'm wrong. There used to be 3 different interpreters for const eval, but now there's only one.
Oh yeah. I only knew of Miri since there was a const one.
And so Miri keeps track of provenance and like whether bytes are initialized or not. So if you read from an initialized memory, for example, Miri will catch that. It'll catch a bunch of things you're not supposed to do in unsafe code. And it'll catch more things than are actually UB. So sometimes Miri will complain and it's actually fine. And then you just go yell at the people who maintain Miri and they're like, oh, there's 2 of us. So it's fun. But Miri is super useful. So this is why you want to run it for all unsafe code you write, really.
But the downside is that it's still a sanitizer. It can only catch rule breaking that it sees. So it can't statically analyze things. It only generally dynamically.
It's a runtime sanitizer. Yeah.
What's that?
It's not a static analyzer. Yeah.
It's a dynamic. It's a sanitizer basically. So you still have to have tests that are exhaustive enough to actually trigger all of the potential UB. But you hit this line on every packet that you receive. So I think it would have complained by now. So. This also seems tedious because you go, well, do you have to write those manual things for every single different kind of socket you have? Like, And it turns out it's one of those things, if you have a function pointer, so what a vtable really is just a struct of function pointers. So all of those functions that you saw so far end up becoming just function pointers in my struct, and they're specifically thin function pointers, whereas not like din trait methods and things like that. But you can't really have a generic function be a function pointer because it hasn't been monomorphized yet. It could be of any type at this point. So it's
James,
not.
you know my job is to stop you and explain what the heck you're talking about, right?
That's true.
Do you know how many things I have to explain right now?
Okay. So when you have a generic function, it actually it's more like a template. It could be for any type. So to get a specific, to tell the compiler, hey, please make me a real function of this, you have to fill in the specific type, and that process is called monomorphization. You're taking it from the generic any to one specific creation of that function.
And then I'll take thin pointer versus wide pointer. Thin is just like, here's where it is in the code. Here's where it is in the executable. And wide pointer has extra metadata added to it. In the case of a closure, it's the environment. So if you're capturing some variables in a closure, that's going in the extra part of the pointer.
Yeah.
But your pointers are only one word
Yeah,
wide?
one pointer. They are one pointers wide. Whereas a wide pointer would usually be like a context pointer and a vtable
Usually be
pointer.
two, but it's not guaranteed.
Yeah. And the thing is, you can actually take any generic method and do the monomorphization on demand. So you could actually store this. You could say, this is my function. So I could take my generic function, which had a t parameter before, and if I say what the specific type is, then I could just stamp out one of these functions on demand, and I can turn that into a normal function pointer. So if I have my socket vtable, and I mentioned some of these are optional, so if you had a socket that for some reason couldn't accept one or the other, these can be options, but because they're pointers, they still are only one word wide because you can't have a null function pointer. So this is a 4-pointer vtable. I could just go, hey, in my impls socket for a given t, I can have a const function vtable. And so if you say I want a socket of type that receives for type t, I can call the const method : vtable and ask the compiler very kindly to stamp me out a copy of this vtable monomorphized to all these specific ones. So actually, when I say open me up a socket of this type, the compiler just stamps me out a vtable, which is actually very similar to how under the hood async works. I was
about to mention it.
Yeah. Async is one of the places under the hood in the compiler where you still have these manual
the
vtables.
Raw vtable. Yeah, but they didn't make them generic, so they can't do the nice things you did. And it's too late to change it.
Yay. So if you want to const your type vtable, you can just stamp out your type and, hey, look, we can get this. And so what actually all of these ones, so I showed you the live versions before. These are all the real versions. So receive owns gets 2 non-null pointers, one for you and one for the type that you're going to receive. Still, you get a real header and you get a real type ID. You get receive error, which is just the only lie there is pin mut self is a non-null pointer. Receive raw, because I'm actually just passing bytes in, it still gets to be mostly real. And receive borrowed, this is the one that I said that I didn't super explain that before, because actually you get, this function gets past another function pointer, because we don't know how that type is storing the data. We know for a borrowed thing, we know it's going to serialize into it. But if you don't know what you're serializing into, how do you have a function that just works for serializing into an area? Particularly for like on the desktop, I might serialize into a vec, and embedded, I might serialize into a queue.
Wait, so is the problem the output or the input?
I've decided that I want to hand you a borrowed message. So I need to actually pass you both the item and a function that will serve to serialize this message.
Why isn't that a method that's provided? Like it's a utility method, right? You could also just serialize it yourself and then just pass the U8.
But the reason is because
it's not typed anymore.
I want to cheat and be extra efficient, so I might want to like pack this into a tiny queue and things like that. So I actually need to call a function with the, hey, I've set up an like a chunk in my ring buffer for this. So I don't need this to happen immediately. I need to apply this at a second stage after I have set up room for this. So at first I need to go into my queue as a socket. I need to go into my queue, go, hey, do I have some room for some bytes? Yes, I have some room for some bytes. So I've set up some room for my bytes. And then I need to serialize into that space, see if that worked. If that worked, then I can say, yes, I have successfully received that message.
I see.
And this is chasing not really performance, but the flexibility to be able to do wildly dynamic things without being able to just say, just shove it in a vec for me.
Right. I should have asked this like 25 slides ago, but like your functions are named receive, and then you give them stuff. So like, is it from the perspective of the network stack? Like,
so from the perspective of the socket, they are receiving. So the way is the socket exists. Someone passes a message, so it either comes in from outside or someone sends it locally. It goes through routing, and we decide that it goes to this socket. And that socket is receiving the message, and then the actual user then receives from the socket on the other side.
Right, so this is not actually a public-facing API or anything. Like,
no, this is all the internal guts of the... So users never see anything like that. Like if we go back a million slides back to that fun example, a seizure warning. Here we go. So the user just sees like serve, which basically is like a raw receive call that just gets the data back out. And then when you go to reply, it actually gives it back to the net stack and says, hey, I'm sending this response back to the source that was given to me.
Right. This sample has serve blocking, but I'm assuming you have serve async or...
Yeah. So right now, actually, yeah. So serve blocking in this case is maybe a little misleading because you await until the message is received, but then in actually processing the endpoint, there's no awaits in the process of handling this message.
I see.
So you're just blocking, going to hand that back. So the regular serve, you're allowed to do, like if you had to get an async mutex while you are processing this request, you could. But in both cases, there's an await at the end of it because you're awaiting for the message to show up. Right. And then the question is just, do you need to do async things to process that message?
Makes sense.
Let's fast forward. I think we were almost done. I think it might be the last two slides. So the whole point here is that I've made this strongly typed network stack in a language that is strongly typed, but it turns out to make my network stack strongly typed, I had to bend the language a little bit to not be quite so strongly typed.
A little bit.
There may have been some unsafe that has happened here. But even though Rust is a strongly typed language, unsafe, anything is possible. So we can still get the outcomes.
The church of unsafe, yes.
So that is a type erasure in Rust in Urgot.
Well,
any parting questions, Amos? Or just a lot of parting questions?
That's quite something. I feel like I'm missing the overall context of like, I don't know. You only have one code sample from the outside, so yeah. Have you built something fun with it?
So yeah, the whole idea is that we want to treat very tiny computers like they're computers. And so when you want to talk to a computer, the way that we've generally figured out to talk between computers these days is with sockets. So you need some way of treating devices over the network. Yeah. But these little devices may not be like your traditional Ethernet or Wi-Fi. It might be over a USB cable or over a serial port and things like that. But kind of the whole running goal of Urgot is to be able to have this network of tiny computers down to like a little microcontroller that has 8K of RAM and 32K of flash and a single core processor. And it can still be a part of this network with devices much, much bigger than it. And those devices can talk to these very tiny devices without having to use a very tedious and painful, like bespoke interface of doing that, of just, hey, I want to throw some Rust data. I want it to find its destination, and I want it to come back. So whether you're a robot arm or spinning a motor or blinking some LEDs, you can just go from your Rust application, hey, send a query to this one to get its current sensor value. Or, hey, set the brightness to max right now. And then you can come back and go, yes, I've got a response with a very like normal feeling, like I said, kind of like Tower, where you have a request response pattern.
You're describing like theoretical possibilities. My question is, do you finally have home automation? Because we did an episode about home automation, and I explained how I went through all the commercially available solutions and how it was a nightmare. And you were like, oh yeah, I was building my own stuff, but then, I've been building my own stuff for like a decade, and it's...
Do you ask someone with a hobby car how far they've driven lately?
All right, well, it's been a pleasure.
The answer is there's some lovely demos. So if you go to the Urgot repo, there's some lovely demos of streaming accelerometer data. The answer is I found more yaks to shave. And perhaps that's sort of the whole point here. I might be inventing a new dressing scheme. What's that?
Will there be a season 3 of self-directed research?
We could do an entire season 3 on just Urgot. I'm trying to avoid doing a whole season 3, but there definitely will be a season 3 of it.
All right, cool. Well, thanks for the presentation.
Thank you very much. I don't know if you brought any stickers, but I have like 10. I've got some postcards.
I have lots of stickers. Yeah.
So if you want a self-directed research sticker or postcard, come and find one of the two of us over the next day or so.
Just sneak in and open my bag and just sit there somewhere.
Excellent. Thank you very much.